Thank you very much, Ben. So I am talking to you today from unusually sunny Glasgow. But the work that I'm going to talk about today was done at another Scottish university, the University of St Andrews. So I just want to point that out and give a shout out, and you will see their logo on all of my slides today. But first, a little bit about my research background to give you a bit of context as to how I approach my work. I'm a synthetic inorganic or organometallic chemist. Most of my background has been with F-block metals, including uranium and thorium. And a lot of this work has to be carried out under inert atmosphere conditions. So this involves the use of inert atmosphere glove boxes and shrink lines. So that's my kind of bread and butter. But after doing this for a while, I decided I wanted to try my hand at something different, and I decided to join an organic chemistry group looking at catalysis. So I joined the group of Dr. Alan Watson, and this allowed me to brush up on some of my skills I hadn't used for a while, so some column chromatography, some TLC, although I still was using metals, so I did still at least get the nice pretty colours. But it also forced me to face one of my greatest fears in life, and that is not in fact clowns, but the use of balloons for inert atmosphere chemistry. So this was pretty standard protocol in this organic chemistry lab, but as you will see, it became necessary to use some of my old faithful inert atmosphere techniques. So the chemistry I was looking at was some cross-coupling catalysis, which we should all be pretty familiar with. I've shown you an example here of Suzuki-Miura cross-coupling, which is palladium-based. So cross-coupling is generally a metal-based catalysis process, which has some similar steps depending on the mechanism. So it will have oxidative addition step. It tends to have a transmetallation step by which aryl boronic acid, which the arine group is transferred onto the metal. And then we have a reductive elimination step whereby a reductive elimination occurs between the two strongest ligands on the metal center. And this yields a low energy, charge neutral organic molecule. The particular type of cross-coupling that I was looking at was actually a copper-based cross-coupling called Chan-Lam mechanism. So this is a CN type cross-coupling. It has a couple of different features that I want to point out. So it does have a transmetallation step. Importantly, we have to have a copper hydroxide ligand in order for the transmetallation to occur. Then we deprotonate the amine ligand to form an amido anionic or X-type ligand. And then cross-coupling is going to happen between this amido ligand and the arine. Importantly, copper 2 doesn't oxidize to copper 3 readily, so we have a disproportionation step where two equivalents of copper 2 react to give a copper 3 high oxidation state intermediate, from which the reductive elimination can occur, forming the carbon-nitrogen bond and yielding a copper 1 species, which can be turned over, usually using oxygen from air. So the important things are that we need two equivalents of copper. We need water for the transmetallation step, and the coupling happens between an anionic nitrogen donor and an anionic carbon donor. But before I started in the Watson group, a discovery had been made by Julian Vanteroo. So he had reacted an aryl boronic acid with copper triflate in acetonitrile, and he found that he obtained an aryl amide. So there was two potential ways in which this could have formed. The first and kind of boring option is that the nitrile could have been hydrolyzed by water, catalyzed by the copper triflate to give an amide, which could then undergo cross-coupling with an aryl boronic acid. And this is a known process for Chan-Lam cross-coupling with amides. And that would have given the amide. Alternatively, we posited that the nitrile has its own lone pair, so it acts as a ligand for the copper itself. And in theory, that could cross-couple with the aromatic boronic acid to give an aryl nitrilium. Now, these nitriliums are known, but they're very highly reactive, and they hydrolyze very readily in order to give amides. So the question was, which mechanism is this procedure going by? And Chao Zhu, a postdoc in the Watson group, did a test reaction between an aryl boronic acid and deuterated acetonitrile and protonated acetamide. So this should be able to differentiate whether we're getting reaction with the nitrile or the amide. And indeed, we only saw arylation of the deuterated, or we only saw the product of arylation with the deuterated species, telling us that, in fact, we are going through an aryl nitrilium, and we're not just seeing cross-coupling with the amide. So what could the mechanism for this be? Well, we based the mechanism on the Chan-Lam one I've shown you before. We knew that the starting material was this bis-triflate, bis-acetonitrile, bis-aquo complex, because we were able to fish these crystals out of the reaction mixture. And if we lose one water molecule from this complex, we have an active site which can undergo transmetallation to generate a copper arene bis-acetonitrile triflate. This can undergo disproportionation to yield a copper 3 bis-triflate aryl acetonitrile intermediate. And our theory was that, the important thing was that this reaction only works with copper triflate. And the reason for that is that usually cross-coupling occurs between the anionic ligands because they are the strongest donors to the copper. In this case, triflate is anionic, but it's not a very strong ligand for the copper. Even though the acetonitrile is charge neutral, it's a really good donor to the copper center. And so in this case, with weak triflate ligands and a strong nitrile, cross-coupling can occur between the two strongest ligands, which are the arene and the nitrile, to generate the nitrilium. So that would give us a copper 1 species, which in theory can be turned over using air. Now, do we have any evidence for this mechanism? Well, we did some high-resolution mass spectrometry on the reaction mixture, and we can see species that represent several of those intermediates, including the nitrilium, but we should be cautious about this because this could form from fragmentation of the amide, which forms from hydrolysis. Okay, so I was tasked with coming in using my inert atmosphere skills to trap the aryl nitrilium. And the reason for this is that aryl nitriliums or nitriliums are really useful CN synthons, and they can be used for lots of other heterocycle forming reactions and a whole range of other useful transformations. The first thing I did in order to study this was to make some aryl nitrilium by a stoichiometric method. So I took an immunyl chloride and treated that with trimethylsilyl triflate to generate the nitrilium on a gram scale. And then I wanted to see how stable this nitrilium was under the reaction conditions. So I first reacted the nitrilium in acetonitrile with copper triflate. Now, just to be clear, this acetonitrile was obtained from a solvent purification system, so it was anhydrous when it was obtained. And in addition to that, it was stored over activated molecular sieves for 48 hours before use. The copper triflate was purchased anhydrous and was not opened outside of an inert atmospheric glove box. So it was only opened under argon, and it was in fact a white powder. As soon as you open copper triflate in air, it starts to turn a pale blue as it becomes solvated by water in the air. So the important thing was I did a treatment of the aryl nitrilium with dry acetonitrile and dry copper triflate, and I saw no reaction whatsoever. On the other hand, if I treated the aryl nitrilium with the crystals of the aquo complex that we fished out of the reaction mixture, I saw immediate formation of the amide through hydrolysis. So it was clear to us that hydrolysis was going to be a very rapid process, and we were going to have our hands full trying to trap the nitrilium. Part of this task fell to Jamie here, who did probably over 50 reactions, looking at intramolecular and intermolecular trapping of the nitrilium. So in a whole host of different ways. Unfortunately, precisely 0 of these reactions were successful. And this leads us to conclude that hydrolysis of the nitrilium occurs really rapidly in these reaction mixtures if we have hydrated copper. Probably the nitrilium doesn't even leave the coordination sphere of the copper before it is hydrolyzed. So we next turned our attention, since we didn't think we could isolate the nitrilium, we started looking at sp2 hybridized nitrogen donors, so still charge neutral. And we looked at dimethylaminopyridine as a strong Lewis base. And in the presence of copper triflate and an RL boronic acid, we were able to isolate the N-arylated pyridinium salt and get crystals of that. And this is quite a robust procedure. So we can confirm that we are indeed cross-coupling to create ionic products. And when they don't hydrolyze, they're able to be isolated. Now, as an inorganic chemist, I really hate substrate scopes, so I'm going to keep this to the bare minimum. The electronic properties, so the more Lewis basic N-partner donors seem to give better yields than those that are less Lewis basic or less electron rich. But we can also use different types of aromatic heterocycle and non-aromatic heterocycles, and in fact non-heterocycles as the N partners. For the RL boronic acid, the electronics have slightly less of an effect in this case, and we can cross-couple to traditionally challenging boronic acids, so those that are sterically bulky around the C center, or heterocycles and alkyls, albeit in lower yield. So sp2 hybridized cross-coupling to give pyridiniums and imidazoliums was quite successful. We next turned our attention to coupling to sp3 hybridized nitrogen species. So we started off with quinacridine, and we weren't sure what kind of product this was going to give us. It could have given us the N-arylated ammonium salt, or it could have undergone hydrolysis to form the ring-open species. Unfortunately, when we did this reaction, we didn't see any of that, and we didn't see that with any of the different amines that we tried. So we tried a whole host with different pKa's and different steric properties, and we didn't see any reactivity. The only one that works is the pyridine in this instance, and that's cross-coupling occurring at this position. This was quite surprising to us because, according to our mechanism, we believed that the rate determining step would be the disproportionation step. And according to our understanding, the stronger the Lewis base on the copper, the easier it should be to oxidize it to copper-3. So this was a little bit perplexing. But then we realized that amines can actually undergo a different reaction with the copper. Amines can undergo oxidation, and this is a process that pyridines and nitriles don't really undergo. So copper-2 triflate can react with a tertiary amine to form copper-1 triflate and an ammonium triflate salt, which is a radical. So we looked at some EPR studies to confirm that this was what was happening in our reaction. In the spectrum shown here, the black line just represents copper-2, so this is just pure copper triflate in acetonitrile. And then with different amines, you can see that we progressively see less and less copper-2 present. So with the timida, which is a bidentate ligand, that kind of retains a lot of copper-2 because the oxidized radical stays within the coordination sphere of the copper, and so it's a reversible process. But with all of the other species, we tend to see a strong degradation in the amount of copper-2 present. We also looked at reactions where we would add the amine as an inhibitor for a process that we already knew worked, and that was the cross-coupling of the RL boronic acid with the dimethylaminopyridine. And so we tried this with 3 different amines. And these different amines have different pKa's, but they also have different redox potentials. The yield of the cross-coupling of the boronic acid with dimethylaminopyridine is 89% when it's uninhibited. So you can see that the dimethyl-aniline is inhibited to a strong degree, whereas the N-butylaziridine is not really inhibited very much. This tracks really well with the oxidation potential of the aniline versus the aziridine, which is the aziridine is very hard to oxidize. But it doesn't really track with the pKa's, whereby the quinacridine has the highest pKa. So that was a really neat explanation for why the sp3 hybridized bases are not undergoing cross-coupling. Now, I want to talk briefly to you about the role of water in this reaction, because I think it's really key to exploiting the potential here. The cross-coupling with the nitriles can either be done in acetonitrile as the solvent, or it can be done by adding a nitrile to a toluene solution. Now, both examples were optimized, and in both cases, it was found that several equivalents of water were necessary for the optimal reaction conditions, the optimal yield. And this kind of makes sense because we know that water is required for the hydrolysis, so we do need one equivalent of water at least there. Water was also was not found to be required, for the cross-coupling with the pyridine. So again, that can make sense. You say 0 equivalents are required, that's fine, because we're not doing hydrolysis here. So if we want to isolate the nitrillium, why can we not just do the reaction with 0 equivalents of water? And if there's no water around to hydrolyze the nitrile, there will be no formation of amide. Well, it's not quite as simple as that, because as I mentioned before in our mechanism, water is necessary in this reaction for the transmetallation process. So we have to have a copper hydroxide ligand, which can transmetallate the aryl boronic acid to form the copper-arene bond. So if we do need water, how come the N-aryl pyridinium can form with no added water in the reaction? Bearing in mind that the toluene is dried, is very dry, very anhydrous, so is the copper triflate, so on and so forth. Well, this comes down to another part of the reaction, which is the boronic acid. So boronic acids are known to undergo condensation reactions, whereby they form this baroxene molecule, which is a trimer. So each molecule of boronic acid can release one equivalent of water. So in the NRL pyridinium reaction, although there's 0 equivalents of added water, there is actually one equivalent present, and this enables the transmetallation to occur. Indeed, if we try the reaction between dimethylaminopyridine, copper triflate, and a third of an equivalent of baroxene, we see no cross-coupling present. So we cannot form the nitrillium simply by eliminating water, because it's required for the transmetallation. So there's a balance to be had here. Okay, so finally, I just want to talk to you briefly about turnover of this reaction. I've shown you the mechanism previously. This is just a summarized version. After reductive elimination, we obtain a copper-1 species, and copper-1 is known to be able to transform into copper-2 with oxygen. And we've even tested this by making the dimethylaminopyridine adduct of the copper-1 triflate and treating it with oxygen, and it does in fact form copper-2. However, when we tried to reduce the stoichiometry of copper in our reactions, we did not see catalytic behavior in the presence of oxygen. And I want to argue to you that I think this is down, again, to our problematic water here. When we have a stoichiometry of 3 equivalents of copper per reaction, we have a sort of almost one-to-one stoichiometry of water to copper. As soon as we reduce the copper stoichiometry, then the water ratio increases dramatically. So this water comes from added water, but it will also be present because of the water in the boronic acid. And so this is going to have a detrimental effect to the yield. And the same thing happens with the pyridinium cross-coupling. If we reduce the stoichiometry, we cannot obtain yields that demonstrate catalysis occurring, and this is probably due to the impact of water on the reaction. Okay, so just to sum up what I've told you today, I've shown you that we can cross-couple to charge-neutral N donors or nitrogen ligands, including nitriles, which is a kind of aryl-Ritter type reaction, and pyridines, imidazoliums, and so forth. The cross-coupling to the nitriles yields amines, but cross-coupling to sp2 hybridized N hydrocycles yields cationic species that are high energy and can be utilized in further reactivity. Coupling to tertiary amines does not occur because of amine oxidation, and water is a key factor in this reaction, and the transmetallation step may have to be is a challenge to be overcome in order to optimize the full potential of this cross-coupling methodology. So all that remains for me to do is to thank the people who supported me in this work, primarily Alan Watson, who is my supervisor on this project, and I think we had a really great dynamic in talking about ideas for this work. Julian Vanteroo, Jamie Fife and Chow Zhu all worked on this project for time periods, and their work contributed a great deal. I want to thank the group that I worked in during this time, and our collaborators, Bella Bode and Alex Slavin. And I want to thank the organisers for an invite, and you all for coming along and hearing my talk, and I'd really love to take any questions.
Fantastic. Thank you for a great talk. We'll go through just a couple of quick questions here. So can you talk a little bit about it? This seems like a very versatile method. This is for me as a chemical engineer, so maybe I'm completely wrong. But it seems like the general strategy that you've developed here is, again, pretty versatile. Is that an accurate statement or no?
So I think that the main limitation, as I've discussed, is the water. And I think that it's not far away from being extremely versatile. I think the water is the main hurdle to overcome. And once that has been overcome, I think that there's quite a lot of potential to extend this cross-coupling to other elements, or it's heterocycles or non-heterocycles of other elements. So I'm thinking phosphines, I'm thinking thiophenes. I can see quite a lot of potential, and what I really love about this is the potential to keep something in a high energy state to do kind of cascade reactivity with it. I think that's a really unique selling point of this method.
Yeah, absolutely. So do you have some ideas for how you might overcome the limitation of the water?
Yes, I do. I do have some ideas, and I'm actually actively working on them in the lab right now. So
fair enough.
Watch the space.
Absolutely, that's fantastic.
Yeah.
Well, I think we'll have to unfortunately have to cut it off here. But thank you very much for the presentation. Like I said, especially for someone like me who doesn't really get to go deep into chemistry. It's really interesting to see the work that's being done now, and the scope that it covers. It's just absolutely fascinating. So thank you again for agreeing to present, and really appreciate it.
Yeah, thanks very much. And I look forward to seeing some more later today before I do hit the hay.